So the motivation, of course, is that we do have accelerators now. They're here to stay. We won't get rid of them anytime soon. So we have to do something to make MPI aware of them. Basically, you all know this probably. The host, a thread on the host or multiple threads on the host control the device through queues or streams. They put work in the stream and eventually get executed on the device. The data gets produced in device memory, so there's a separate memory space. In many cases that might change at some point. But MPI will take the data out of the device memory space and put it on the network. We do now have some form of exposure of memory spaces in MPI with the new info keys that were introduced. Also through the site document that will be part of what will be attached to 4.2, where you can say what memory spaces you're actually going to use. But MPI is blissfully unaware of execution spaces. So the only thing you can do right now is to fully synchronize the stream before you start sending data that was produced on that stream by a previous kernel. And that has correctness implications. So we exclusively interact with the host execution space, and that is typically the thread that calls MPI. So a blocking operation will block the calling thread until the data is available or data has been read, and you can override it. Non-blocking operations are actually ordered with operations on the thread that came before, so there are memory barriers, and so the data is available to the NIC before we trigger the communication. But for, as I said, for streams, work on the GPU, we always have to synchronize. Because otherwise, what will happen is in the left part of this picture there, we submit a kernel, we synchronize, and then we do the send. Everything is fine. If we forget the sync, then the kernel will overlap with the send, and we will get inconsistent data, which is probably not what you want. So there's two reasons why we want stream awareness. One is correctness. It exposes the device execution space to MPI, so that we see consistent data and avoid the errors that we've seen, and we've actually had users in OpenMPI that were complaining and asking for how to properly do this. And so we can order the network communication with what happens on the device, but also for performance reasons, right? So the host keeps pushing things into the stream, and if we have to synchronize, that means that we basically run that stream dry. For the time when we execute the send or ISend, nothing will happen on that stream, because there's no, we cannot overlap anything. So instead, if we get away, we have a way to enqueue communication operations onto the stream. We can keep submitting into that stream so that the device remains busy, and potentially overlap work on the device with what happens on the network. Of course, you can use multiple streams, but then again, there's no synchronization there. So we've talked about, or this morning we had a session on partition operations and how that can be used to trigger transfers from the device. We set up everything on the host, and then on the device we just ring the doorbell on the NIC so that the transfers start. We still need to do the work on the host, right? We still need to start on the host, we need to complete on the host, we need to start again. So those things could be integrated into a stream. You integrate this, or you enqueue the start onto the stream, then you trigger your operations, inside the kernel, and then you enqueue await onto the stream, and then you can do that. You can basically push a lot of things onto the stream. You never have to do that from the host. So this is the stream integration that we're talking about here is complementary to the device side partitioned operation. There has been work on device bindings for MPI. I think it was called Device Everywhere or something like that. I forgot the exact name. That was presented last year at EuroMPI, something along those lines. It is tricky, right? MPI is complicated. There's a reason why Nickel doesn't use tags, because tag matching is expensive. Doing that on the device is hard. So we don't really think, or I don't think that this is a way to go for MPI. And of course, I'm not telling you anything new here. This two pieces of work that came out 2 years ago. I think both of them actually. That try to accomplish this integration streams, and I'm going to go over them one slide each in a second. But basically, what they have in common is that they offer some new MPI object, a stream or a queue. Things are then enqueued into that stream or the queue, and it requires a duplication of the API. We basically we get enqueue operations for all MPI operations that are in the standard. And to some extent, they all rely on strong progress as far as we could see. So the streams proposal from EuroMPI, which we was the author of, it creates a stream from an info object. That info object has a hex string that encodes the stream, or the CUDA stream or HIP stream or SYCL queue. That then gets passed to create a communicator, and on that communicator we can enqueue send operations. Kind of convoluted, but it's also been proposed for broader use with multi-threading through some sort of multiplexing that is kind of orthogonal to the problem of GPU streams. And Patrick mentioned this proposal, the enqueue operation that was published by Naveen from HPE. That's the HPE proposal I think Patrick mentioned. Here we create a queue object and then enqueue things into that queue object. We start the queue. So when we start the queue, that submits all operations that we've integrated or that we've put into the queue onto the device stream. And then we wait for the queue to complete. So there's a queue that interacts with the stream. Anyway, so in this work, we try to explore a possible design that reduces the amount of points that we have to touch in the standard, and basically presents a minimal extension that we could come up with. And I was chuckling when Patrick said that the EuroMPI proposal changed the semantics of MPI send, until I realized that we're doing exactly that. So I'm sorry about that. We do, but I will explain how we do it, and for us at least, it makes sense. So the question is, do we want to add like another level on that axis here that is blocking, non-blocking, persistent, partitioned, now queue, right? Or do we say we kind of integrate stream support for all of them so that you can use the existing semantics in the context of a stream? So we do have communication contexts in MPI, right? We have communicators that provide process mappings and communication contexts. Usually there's network context attached to them. We have windows that hold memory and the context for RMA operations, and files, of course, for I/O. And then we have well-defined semantics for blocking, non-blocking, persistent, and partitioned operations. Blocking operations, of course, there's a FIFO start and completion. Non-blocking is a FIFO start, but at deferred completion, at some point it will complete and you can go do other things. And persistent and partitioned is you have a prior setup, everything's fixed, and then a FIFO start and a deferred completion. What we realized is that stream integration is basically a non-blocking operation, right? You start an operation at a deferred time with well-defined semantics. So it starts once the queue or the stream reaches that point. We associate streams with communicator files in Windows. That basically transfers the execution space, or it changes the execution space that the communicator is aware of. It's not the host anymore, it's the stream on which the kernel work happens. And then you enqueue operations onto that execution space, that stream, using the existing operation. You can enqueue await if you use non-blocking or persistent operations, and eventually you synchronize the stream, and we need a dedicated function for that as well. So we can set a stream on a communicator. It's passed via a void pointer that basically points to, in our case, a hip stream T and a string that says, well, this is hip. And then we also added info for future extensions. But what's important is that you get a flag back that says whether the implementation knows this kind of the stream. If OpenMPI was built with CUDA, we are not built with HIP, and you pass us a HIP stream, we can say, I don't know about this, better do something else. So there's a fallback opportunity if the implementation doesn't support it. And there's a way to query a stream that is potentially associated with a communicator. So if there was one associated before, you can get that stream back. And you can reset a stream on a communicator. So if you that will not synchronize the stream, it will just mean that now you're working on a different stream with that communicator. Once that communicator is aware of that execution space on the device, you can enqueue operations into that execution space. And here we reuse the existing semantics, right? So an MPI send enqueued into that device execution space will block the execution space, but it will not block the host thread. So from the perspective of the host, it becomes a non-blocking operation. And I'm sure there can be a lot of arguments made about this, but it will, the blocking nature of the call will transfer to the device execution space. It will block the stream. You can still enqueue operations onto that stream, but they will not be executed until before the send is complete. So the operations will be pending on that stream and prevent subsequent operations from executing. Right. So non-blocking operations are similar. So an ISEND will be enqueued on the stream. Once the ISEND gets triggered on the stream, any subsequent kernels can already start executing. So you can get an overlap between kernels on a stream and the send that happens on the network. And then we need to enqueue await. And this is one of the few functions where we kind of deviate, because
we also offer you a chance to wait for the operation on the host. So you get a request back from the ISEND, and now you could block the host thread until that ISEND is complete, or you give it back to MPI through the stream wait, and that will block the stream at that point until the ISEND is complete. So yeah, and the same applies to persistent and partitioned operations. If you call when you create a persistent send, the stream that is associated with the communicator will be associated with that send. So it will, the start that you call on that request applies to, or will be enqueued into the stream that was associated with the communicator. And then again, you can enqueue a wait on that stream. And so you can enqueue start and wait on the stream and potentially get overlap with kernels on the stream as well. And that ties in with the device side triggering of partitions. That's a nice extension. As I said, we need the stream wait to return the ownership of requests back to MPI. And we differ here because we want to allow the host to block on the wait if the application wants to know on the host side when an operation on a stream is complete. So that's why we have a separate mechanism for that. The stream wait itself does not block the calling thread. So again, that's just a submit in a way. And then we realized that we cannot rely on strong progress. Everyone gets, or many people get unhappy when we spawn a separate thread that keeps polling. Everyone wants progress, but no one wants to sacrifice a core. So we can't really do that. We also don't know what the implementation does, like HIP or CUDA. We cannot really rely on progress there. So we need some form of combined progress. The application basically has to progress MPI while the stream is not complete yet. So that's why we have MPI sync stream. It synchronizes the stream that is associated with the communicator and progresses outstanding MPI operations. We found that we couldn't make it work otherwise, except for spinning up a progress thread. Here's an example of what that looks like in practice. So here we submit memory allocation, a kernel. Then we set the stream on the communicator. In this case, just MPI world, and make sure that the implementation actually understands it. Then we submit an ISEND onto the stream and the mem copy. So the ISEND and the mem copy can run in parallel, right? So we can transfer data to the host while sending it on the device from onto the network. And then we enqueue a wait onto the stream and a free, and eventually we synchronize. So all of this now happens in the correct order on the stream. So we have an implementation that's on the web, on GitHub, if you're interested. We've only implemented persistent and non-blocking operations. Blocking operations are trivial to add. I might do that at some point. And as everyone else, we only focus on send receive, but the same mechanism will apply to collective operations. It's based on my own branch of OpenMPI, which has continuations that have been around for a long time now, simply because it made my life easier to have callbacks for MPI operations. But we're working on a generic implementation that we could use with Cray MPI, for example. It's almost done. I wanted to present data, and it hasn't worked yet. We are using generalized requests for the user-facing request. So this is implemented as a PMPI layer. We didn't put this in any implementation. It's just a proof of concept in a PMPI layer. So user-facing requests were useful there. We don't launch a kernel. We only synchronize, or we use some form of synchronization mechanism that HIP offers us. One is to launch a host function. Basically means that once the stream reaches that point, the CUDA progress or the HIP progress thread calls our callback. And then once the callback is done, the kernel continues executing. Or we can also use events where we poll on an event, and once that event occurs, we do the send or receive. So in that case, the stream will continue past that event. It's not blocked. And then we can block the stream using HIP write value and HIP wait value. So that if we have to block, for example, because of an enqueued wait, the stream will be blocked with wait value, and then eventually we'll write one. We do have optional progress thread support, but that the performance was terrible. I will show that in a second. And we actually experimented with graph capturing support. So maybe you've used that before. In HIP and CUDA, you can set the stream into capture mode, where everything you enqueue on the stream will be captured, and you can replay that. So you don't have to enqueue everything at once individually. There's some potential optimizations that are possible. And we were able to integrate these MPI operations with the stream capturing. The next step would be to work on explicit graph construction, but that's a much more convoluted API. The results are underwhelming, unfortunately. So we came up with our own benchmark because there's no benchmark suit that we could find. We enqueue a kernel where we can control the length of the execution. We enqueue a send or receive for a variable message size, and then another kernel, so that we try to get overlap between send and receive. As you can see here, for very large kernels, it didn't make a difference really. RICL was significantly faster for larger messages because they do the communication from the device, as far as we understand. That was hard to beat with our proof of concept. And if we enable progress threads, then for some reason here the latency increases, and we're not really sure why, because it's not occurring for small messages. But we see some difference here for whether we're using callbacks or events, but that's not really significant. So having a benchmark suite with representative applications that can benefit from enqueuing operations onto a stream would help with the design of this API, or any API that addresses this issue in MPI. And that's what Patrick already mentioned. We thought about whether MPI operations are allowed to synchronize two execution spaces at once. So is the calling thread allowed to block? It's probably a bad idea, because it would turn operations into collective operations if they have to wait on a stream that has a collective operation enqueued. So we can't really do that. We want to add thread-specific binding of streams, so that individual threads that can have different streams associated with a communicator. We can do that through a flag. I think we have an idea of how to do that. Yes, we're working with Carl at Sandia to experiment with this in Cocos.com to see how that fits with that. And then, of course, as I said, the explicit API, graph API integration. So we think so we can get away with 5 new procedures in the MPI versus 150 if we duplicate all the communication API to NQ operations. It does change the semantics, as Patrick said earlier, especially of blocking operations. And maybe we should just ignore blocking operations and only have non-blocking operations supported for stream integration. Because I agree, it's a little weird. But we can reuse the existing infrastructure in MPI, and I kind of like that aspect of it. And then we'll start, hopefully restart the discussion in the hybrid and accelerator working group to get this into the standard in one way or another. We're not really married to this. This was just an exercise for us. And that's it. Thank you.
Well, thanks a lot, Joseph, for this refreshing idea. Any questions? We have time for one, I would say. Martin.
So thank you. I had a question though. I mean, the communicator is a global object. Your stream is a local object in the sense the device is on the local, connected to the local process only. So why the design decision to tie those two together? And then what are your expectations on the other processes in the communicator? Do they have to have a stream as well?
No. Every process can do their own thing, right? If you want to do it on a, if you want to enqueue it into a stream, do it. If not, then not. The semantics don't change, really. The reason why we tie it to a communicator is that this is the communication context, right? And the stream becomes the communication context. That's the context in which the data is produced that you're communicating. So in a way, it seemed natural to us, at least, to not split that in 2 pieces and instead have it in one.
But this would make the set operation the only communicator set operation. I think that's not a collective then, right?
That's a good point. Yes.
Perhaps we should talk about automating. Another, perhaps, other way would be to tie it to a session, which is a local object. That's kind of why I'm asking.
Yeah, but sessions are even more. They're heavier than communicators, right? So we couldn't just change the stream. So one of the things that we realized that I think I mentioned here, the thread specific streams, right? That's a thing that probably users will want to have because you can have like 1 stream per thread and you might want to use the same communicator for it. If you tie it to sessions, there's no way you can do that.
Okay, then thanks again, Joseph.